So let us now try to understand term by term what these acceleration term contain. It has 1, 2, 3, 4 terms. Okay, let's look at one after the another. So I need to draw again actually. So let me draw this one. Okay. So what do you see? Each point P, let my point P be here. So I'm not going to use I cap and j cap since we are using only r cap and theta cap. So it's better we draw this and we write r cap, r vector here. You know the direction of r cap? Direction of r cap is parallel to the direction of r vector, and direction of theta cap is perpendicular to direction of r cap. Okay. The first term in the acceleration is r double dot, and this is in which direction? It is in r cap direction, which is quite obvious. If you have a ball at origin and if the ball is moving along this r vector at a constant velocity, you say the velocity as r dot r cap. But if the same ball is moving along this radius vector r with a non-uniform velocity, then what do you say? You say it has an acceleration and you put another dot above the r. So r double dot r cap represents the acceleration in the radial direction. Second is r theta dot square, and this is also an acceleration along r cap. This is actually the centrifugal acceleration, and with centrifugal acceleration there is a force if you multiply mass with it called as the centrifugal force. That is, if you have a center and you have a ball tied to the center through a string, and if the ball is moving along a circular motion, then it experiences a centrifugal force that tries to push the ball away from the center, and the tension balances this centrifugal force. Okay, so either you can call it centrifugal or centripetal, whatever, but this is also an acceleration. But when does this acceleration happen? This acceleration does not contain any double dot. Quite interesting, right? Because if you remember the expression for centrifugal force, it was force is equals to m v square divided by r. If you remove the mass, then you get centrifugal acceleration, which is v square divided by r. Now what is v square? V square is r square omega square, so you'll get r omega. But what is omega? Omega is theta dot. So you see r theta dot is actually the centrifugal acceleration. So when a body moves in a circular motion, even with a constant velocity, constant tangential velocity, there is a force always acting towards the or away from the radial direction. Okay, so these are the two forces in the radial direction. That is, if the ball is moving along the radial direction with some acceleration, then it has r double dot, and if the ball is moving in a circular motion, then r theta dot square represents the centrifugal acceleration. Okay, this is clear. Now the next is we have to look at the accelerations that we have with the theta cap. So what is the third term? The third term is r theta double dot, and it is along the theta cap direction. This is also related to circular motion actually. So if you have a center, if you have a ball, and the ball is moving in circular direction in this way. So if the ball is moving at a constant tangential velocity, then there is an acceleration towards the center called as the centripetal acceleration, and also there is an acceleration which tries to throw the ball away, centrifugal acceleration. But now we are not considering that the ball is moving around the circle with a constant omega. We want now the ball moving around the circle with an acceleration. So omega is not constant, but omega is a function of t. So if omega is a function of t, it means theta double dot. So what r theta double dot represents? So r theta double dot represents tangential acceleration, because let me tell you what is tangential velocity. Tangential velocity, as you know from circular motion, is r theta dot. Okay, so what is tangential acceleration? It is time derivative of this, radius is constant, so r theta double dot. It means, so this is nothing but the rate of change of tangential velocity. Okay, and we all know tangential velocity means this velocity. Okay, it means the ball is moving around the circle in such a way that the magnitude of tangential velocity is constantly changing. So consider the ball is moving around the circle with an acceleration 3 meter per second square. It means in every 1 second the tangential velocity is increasing by 3 meter per second. Okay, so clear with the third term? Now let us go towards the fourth term. As you can see, the fourth term also acts along theta cap direction. Remember theta cap direction from here, always remember this. Okay, if you look at the expression, it's quite weird. It's 2r dot theta dot, and it is acting along the theta cap direction. This is the Coriolis force term that I discussed earlier. This is actually the Coriolis acceleration. If you multiply mass with it, it becomes force. So what was Coriolis force? If you remember, Coriolis force, as we discussed earlier, was 2m omega into v tangential. Okay, this was our Coriolis force. So it has, if you remove the mass, then what do you have? You have the Coriolis acceleration. So if you remove the mass, then instead of force, you are going to have some acceleration called as the Coriolis acceleration. Okay, so I hope the various terms in the acceleration here in polar coordinate is clear. Okay, so you see, if we write acceleration in Cartesian form, the information available to us is less. But if we write the same acceleration in polar coordinate, the information available to us regarding the various types of acceleration and their respective forces that a object can experience in various types of motions is quite clear and evident from the acceleration written in polar coordinate.